everybody, get ready to do lesson 3.2 part 2 today of pre-calculus math. If you need note-taking guides or worksheets, email me here and I'll get those out to you. 3.2 logarithmic functions and their graphs. Part 2, we have 6 points here of note-taking, so if you need note-taking guides, contact me. And then a note-taking guide will also include your classwork. So teachers, today's bell work for your students, sketch the graph of f, then use the graph of f to graph g. So basically use f here as your parent function for g students, and then do the same thing down here. Give your students about 6-7 minutes for this one. Okay, welcome back for solutions for today's bell work. 10 points for this. And then for our first bell work, f of x equals 15 to the x, and g of x equals log base 15x, or inverse of each other. So the functions would look like this here. Your log function will do this, and then here is your exponential. They are reflections of each other in the y equals x line that's drawn through the origin. Down here, f of x equals 4 to the x, then g of x equals log base 4x, or inverse functions of each other. And again, they are reflections of in the line of y equals x, which is drawn through the origin, somewhat like that. This is your exponential, and this is your log function. So that's what you should. Okay, we're going to go right into an example here. Example 5, sketch the graph of a logarithmic function. Sketch the graph of the common log function, f of x equals log base 10x by hand. So begin by constructing a table of values. Note that some of the values can be obtained without a calculator by using the inverse property of logarithms. Others require a calculator. So here's your table here without and then with a calculator. As you get more into larger numbers here, you will need a calculator for these. And then these down here, these are just inverses here. And then this is what your f of x equals log base 10x line will look like here. Your log function will look like, should look like that on your calculator. Into a guided practice, find domain, vertical asymptote, and x-intercept of this logarithmic function here, and sketch it. Sketch this graph by hand. Students, this is yours to do on your own. Pay attention up here. Okay, to do our guided practice, our domain here is x plus 2 has got to be greater than 0. Cannot take a log of a negative number, so x has got to be greater than negative 2 here in this situation here. X has got to be greater than negative 2. And then a vertical asymptote for this case here, well, x will equal negative 2. That would be our vertical asymptote here. So when we solve for our y here, for this situation here, log base 2 x plus 2 equals 0. We'll just take a log, log base 2 of 0 would be 1. So x plus 2 would equal 1, and then x would equal negative 1. So in that situation here, that is where you have a 0 here for your, on your x-axis would be when x equals negative 1, y would equal 0 here at negative 1. You're making this equal 0, and that's what you get. You take log base 2 of both sides, and you get x plus 2 equals 1. And then the x-intercept in this case here is negative 1. So to Find what a parent logarithmic function looks like. Log base a x, a has got to be greater than 0, and a cannot equal 1. Here is a graph of that, log base a to the x, and then here are stipulations here for this graph here. Domain is from 0 to positive infinity, range is negative to positive infinity, intercept is 1, 0 here, increasing on the 0 to infinity, y-axis is a vertical asymptote here, log base 8x goes to negative infinity as x goes to positive 0. C positive 0. So as this goes down this way, it goes to negative infinity. It is continuous. And then the reflection of the graph of f of x equals a to the x power, or the line y reflected in the line y equals x. So let's get into another example displaying this. Example 6, library of parent functions for f of x log base a to the x. Each of the following functions is a transformation of the graph of log base 10 x. This situation here, this is log base 10 to the x is here, this lighter line here. And then this line here is log base 10 to the x minus 1, which is this one here, equals f of x minus 1 here. The graph of g can be obtained by shifting the graph of f 1 unit to the right. So we've shifted it 1 unit to the right. So here it is again. Here's a little bit closer examination of it here. And then h of x here is 2 plus log base 10 to the x equals 2 plus f of x here. So the graph of h can be obtained by shifting the graph of f 2 units upwards. So we've shifted this up here just 2 units upwards here. It has the same shape, general shape here, but it's just shifted up 2. That's the difference here. Okay, into our guide practice now. We're going to describe transformation of the graph of f that yields the graph of g. So we're going to go from this graph to g. The graph of g of x equals negative log base 10x is a reflection in the x-axis of the graph of f of x equals log base 10 to the x. So we have a situation here where this is what that graph will generally look like, the general shape of that. And then we started with log base 10 to the x, that's this line here. Then this is just a reflection here in the x-axis. The natural logarithmic function f of x equals e to the x is 1 to 1, so it has an inverse function. The inverse function is called the natural logarithmic function and is denoted by the special symbol natural log x, read as natural log of x, or ln of x. The natural log function for x greater than 0, y equals natural log x, if and only if x equals e to the y. The function given by f of x equals log base e to the x equals natural log x. And it's called the natural logarithmic function. This goes in your notebook, page 6, students, into your notebook. Into your notebook here, page 7, equations. Y equals natural log x and x equals e to the y are equivalent. Note that the natural logarithm, natural log x, is written without a base. The base is just understood to be e because the functions f of x equals e to the x and g of x equals natural log x are inverse functions of each other. So it's just given that natural log is to the e to the x, natural log base e. Their graphs are reflections of each other in the line y equals x. This is another notebook entry, page 7, students, so make that entry in your notebook. Okay, going into our next example here. Example 7, evaluate a natural logarithmic function. Use a calculator to evaluate the function f of x equals natural log x at each of the indicated values of x. So x equals 2. So we're going to plug that in our natural log here. Function value f of 2 equals natural log 2. Graphing calculator strokes would be natural log 2 enter. And then our display would be this number here for natural log 2. And then b, x equals 0.3. So f of 0.3 equals natural log 0.3. Natural log 0.3 enter. Then we get this negative number here. And then c, x equals negative 1. So f of negative 1 equals the natural log of negative 1. Natural log negative 1 enter, and then we get an error message here. Cannot take a natural log of a negative number. Let's go to a guided practice here. Students, this is yours, so pay attention here. Use a calculator to evaluate the function at the indicated value of x. Round your result to 3 decimal places. So the natural log of the square root of 42 equals 1.869. You should get that on your calculator. Students, this is up to you. Properties of natural logs. This goes in your notebook, page 10, students, in your notebook. Natural log 1 equals 0 because e to the 0 equals 1. Natural log e equals 1 because e to the 1 equals e. Natural log e to the x equals x, and e to the natural log x equals x. These are inverse properties. Basically, you have natural log e here, natural log e to the x. These cancel. The x will drop down. That will equal x. And then the natural log e to the x, the e's will cancel. Then the x will equal x here. And then if natural log x equals natural log y, then x would equal y. That's one-to-one property there. Okay, let's go do another example here. Example 8, using properties of natural logs. Use the properties of natural logs to rewrite each expression. Natural log 1 over e. So natural log 1 over e would equal natural log e to the negative 1, which would equal negative 1. So you got natural log base e to the negative 1. The e's would cancel, just become negative 1. Then e to the natural log 5 as an exponent up here, e to the natural log 5. So e to the natural log 5, again you would have an e here, natural log base e 5. That base would cancel with this e here, so the 5 would drop down. 5 would equal 5, inverse property again. Then 4 times natural log 1. 4 times natural log 1 would be 4 times 0 would equal 0, property 1. And then for d, 2 times natural log e. 2 times natural log e, and then again this is natural log base e to the e. Would be that these would cancel, would be 1, so it'd be 2 times 1 would equal 2. That's property 2 for that one. Okay, let's do one of these. Rewrite the expression. So natural log e squared. So using the properties of natural logs. This is yours down here, students. So let's do our guide practice up here. E to the natural log, or rather, I'm sorry, natural log e to the second power. Yeah, basically, don't forget you have natural log base e to the e squared, and then your e's would cancel here, and the 2 would drop down, so this would equal 2. I'm going to let you handle that one. It's the inverse property again. Okay, into our next example. Example 9, finding domains of logarithmic functions. Find the domain of each function. So f of x equals natural log quantity x minus 2. Algebraic solution. So because natural log x minus 2 is defined only when x minus 2 is greater than 0, this got to be greater than 0 here. It follows that the domain of f is 2 and infinity. And then the graphical solution, here is the graph of that, is right here. So, and then here is your vertical asymptote here at x equals 2. The x-coordinates of points on the graph appear to extend from the right of 2 to infinity. So you can estimate the domain to be 2 to positive infinity. So this is your domain over here. Okay, so for b here, g of x equals natural log 2 minus x, because natural log 2 minus x is defined only when what? 2 minus x has got to be greater than 0. This has got to be greater than 0. It follows that the domain of g is negative infinity and then 2. So your graph is coming this way from left to right, and then it hits your vertical asymptote here at 2. The x-coordinates of points on the graph appear to extend from negative infinity to the left of 2. So you can estimate the domain to be negative infinity 2. Okay, this one here, h of x equals natural log x squared. Here is your graph here, natural log x squared. This is h of x is natural log x squared. This is natural log x squared here. What's going on here? The x-coordinates of points on the graph appear to include all real numbers except 0. So this is your vertical asymptote here is the y-axis. So you can estimate the domain to be all real numbers except x equals 0. So you have two parts of this graph, on the positive side and on the negative side here. And they come together here at the y-axis, basically, is what's happening here, natural log x squared. Okay. Because natural log x squared is defined only when x squared is greater than 0, it follows that the domain of h is all real numbers except x equals 0. So there's your domain there, is all real numbers except x equals 0 for this function here. Okay, let's try guided practice here. Find the domain, vertical asymptote, and x-intercept of the logarithmic function, this function here, and sketch its graph by hand. Verify using a graphing utility. So here's a little table for you to utilize. Students down here for yours. Same thing down here. So here is the actual graph of this function here. And your vertical asymptote is x equals 1. Domain is x has got to be greater than 1. There's your domain. And the domain is 1, positive infinity. Vertical asymptote is 1. So here's your vertical asymptote. And then here's your table for your... Okay, now to our next example here. Example 10, psychology. Students participating in a psychology experiment, attend several lectures on a subject, and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group were given by the human memory model, which is right here. And then 0 is less than or equal to t, and t is less than or equal to 12, up to 12 months, using this function here, where t is the time in months. The graph of f is shown. So here is the graph of this function here. Average score seems to fall here up to 12 months. What was the average score on the original exam at time equals 0? So that would be up here, wouldn't it? So for up here, when x equals 0, y would equal 75. So the average score was 75 here when they took the exam. And then the original average score was at time 0 was 75. So now what was the average score at the end of 2 months? So here is when x equals 2, y would equal 68.4. So it drops by about 7 points, 6.5 points. After 2 months, the average score was 68.41. So, moving right along here with this example 10, what was the average score of t equals 6 months? So at 6 months, when x equals 6, we have 63.3 on our test. So after 6 months, we plug in 6 here, 75 minus 6 log, natural log 7. There's our natural log 7. So we had a 63.32 score. So after 6 months, it was 63.32. So we dropped about 12 points after 6 months. So let's go into our guided practice here. Students in a mathematics class were given an exam and then tested monthly with an equivalent exam. The average scores for the class were given by the human memory model, where t is the time in months. What was the average score on the original? So for the original, it was an 80 was the original. So up here 80 minus 17 times log base 10 t plus 1. So f of 0, when you plug that in there, you're taking a log of 1, which is going to be 0. So 80 minus 0. And then you go on from that. And I'm going to let your students do that. That is your lesson for today in pre-calculus math. If you need solution PowerPoints for the homework, email me here. Thank you very much.